Okay, guys, we're starting our chapter 11 journey right now. It is on parametric and polar equations. That's all of chapter 11. And right, so let's start by taking a look at our worksheet here. So we've got Snowpiercer. You might recognize that. That's Captain America right there in the middle. But Snowpiercer, it's this 2013 science fiction movie. It's basically about a train which is carrying the remnants of humanity because of an experiment, and that turned the entire world frozen. So you see over here we got Snowball Earth, which is fun to consider. You got Chris Evans as a member of the lower class tail section, who's leading a revolution against the people in the front of the train, who are the wealthy people. So this is a movie about social revolution, really. Okay, so in order for us to do this, we need to look at parametric equations because well, that's how most motion is described, regardless of what you were told in algebra. So parametric functions are defined by a set of equations with the same independent variable, usually t. For example, we have cosine t, sine t. T is between 0 and pi. Let's go ahead and, first of all, figure out how to graph that. I know you know how to graph cosine. I know you know how to graph sine. We're going to fix one more thing here. This is a typo. That should be 2 pi. Don't worry, when you get your paper, it'll say 2 pi. So we're going to grab our calculator, and this is all very exciting stuff over here. We're going to get to the y equals section. No, we're not. We're going to go to the mode section, and we're going to change our mode. We are going to change our mode over here, function types. We're going to change the function type to parametric. You're going to notice over there that there's also a polar. So that's coming up soon. Don't worry about that. So now when I push y equals, things look a little bit different. You've got cosine t, you've got sine t, you've got x and y. This is a place for us to actually go over here and scroll all the way to the right and push enter, because that's going to give us a few more options. Over here where it says line, that actually, your calculator can graph a whole bunch of lines. So we're going to start from the beginning. This is your normal one, just a regular line, moderate thickness. This is a really thick line. This one over here, it looks like a key, kind of. I don't know what to call that, but it's actually called the path. So that's the path. Over here is the path also, but it just has a floating ball. So it's while it traces out the path, it doesn't tell you where it's been. That's kind of fun to play with, but I'm not going to do it here. You might want to do it on your own time. This is a dotted line. This is another dotted line, and then we're back to the beginning. So when I do these on the calculator for parametric mode, I like to keep it on this path function because it does a couple of nice things. We're going to say OK. Next thing is we're going to set our window 0 to pi. No, we don't want it to go to 0 to pi. We want it to go from 0 to 2 pi. So change that to 2 pi. T-step, this basically tells the calculator how often to evaluate the function. Right now this is evaluating our functions every 0.13 places, or no, every 0.13. So it's going to create something which looks kind of smooth. If you have that bigger, you're going to get really jagged lines, and if you get that smaller, yeah, it'll look nice, but it'll take forever to graph because your calculator is making a lot of calculations. Okay, over here we have our x-min and we have our y-min. I'm going to change that. Let's go from -3 to +3. X scale, we'll keep that at 1. Let's make our y's go from -2 to +2. That'll give me a little bit of a less distorted view. And I'll push graph and make sure you watch what happens. So it traced out the path of this thing, And that circle acted like it was the tip of a pencil, so you got to see where things started and where things ended. So if I get over to my worksheet now and I graph this, which is the next thing we're supposed to do, and of course this thing glitches on me. Okay, so when we graph it, it's just going to look like a circle. So we're supposed to note a few things here. I'll note them along. This is the start. Then it moves along in a circular motion, clockwise, really. Yeah, I know, this is looking really bad. And then that's the finish. Okay. To notate the direction of travel, we usually put arrows on the path. So yay, our Snowpiercer has made a circle. Notice that while both functions are functions of t, this graph is not a function of t. Why not? It does not pass the vertical line test. And yet it is a function. That's a major motivation for using our parametric functions, is we don't have to worry about the vertical line test anymore. So you should be able to graph a few simple ones. We're going to do some simple ones here. So excuse me while I fill these out. First of all, it's probably good for us to graph integer values of t. And then next we're going to go ahead and graph over here the values of x. So when t equals 0, the square root of 0 is 0, 1, 1.4, 1.7, and then finally 2. The y-coordinate is t minus 2, so 0 minus 2 is negative 2, negative 1, 0, 1, 2. Go ahead and plot those points here. The first one is 0, negative 2. Notice 0, 0, negative 2. Okay. So 0, negative 2 is right over here. We'll notate that with start. And then the next one here is 1 and negative 1. Good. 1.4 and 0. 1.7 and 1. And then 2, 2. So this traces out a nice gentle curve, which I've totally messed up with that as the end. We'll go ahead and put some arrows in here to indicate direction of travel. And that's graphing a parametric function. You don't really have to graph anything too, nasty here in calculus. It's just a simple parametric equation. Okay, so now it's time to calculus. First one, the derivative, that should make sense. dy dx is just dy dt over dx dt. The next one is a second derivative. That one doesn't make as much sense. There is some derivation here which you might want to look at, but I'm not going to worry too much about it. We should just know that the second derivative of y with respect to x, that's the derivative with respect to t of the slope equation divided by the derivative with respect to t of x. Okay, I know, doesn't make a whole lot of sense, but we're just going to have to live with it. Example. Okay, so consider the Snowpiercer traveling on a function defined parametrically. X squared equals t minus 5, x equals t squared minus 5, y equals 2 sine t. X is east-west, y is north-south. Find the slope of the curve when t equals pi over 2. Okay, what happens when t equals pi over 2? The slope is equal to, well, you know what, let's do this first. Let's figure out dy dt, because we're going to need that all the way through here. Dy dt is 2 cosine t. Let's figure out dx dt. We're going to need that all the way throughout, and that is just 2t. So those two things are going to be important to us. Let's shove this guy down a little bit and continue. So we need dy dt on top of dx dt. So dy dt is 2 cosine t. Dx dt is 2t. So the slope is cosine t over t. What about the slope when t equals pi over 2? Well, that is the cosine of pi over 2 divided by pi over 2, which is 0. Okay, so the slope is 0. Next, let's maximize y, which means we're going to find the northernmost point on the track. And if we're maximizing and we have an interval 0 to pi, then that means we're using a candidate test. I know it's been a while, so we'll go ahead and figure that out. Candidate test starts with us figuring out our derivative of the function that we want to maximize. So we want to find the derivative of y with respect to t. We already did that. We know it's 2 cosine t. And then we proceed to find critical numbers. So when is cosine t equal to 0, basically? Cosine t is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2. And then here we start weeding out to find anything that is not in our domain. And that's not between 0 and pi. That's not between 0 and pi. So just pi halves. Next part of our test, our candidate test, we're just going to evaluate y at, first of all, our endpoints of our interval, which were 0 and pi. And lastly, at any critical numbers, which was just pi over 2. So sine of 0 is 0. That was easy. Sine of pi is also 0. That was easy. Sine of pi over 2 is 1. So this is 2 times 1, or just 2. We can clearly call that our maximum. So the northernmost point on the graph, on the track, happens when t equals pi over 2. That's our y-coordinate. What's our x-coordinate? X-coordinate is going to equal t squared minus 5, which is equal to pi squared over 4 minus 5. I don't care to simplify that really. So the northernmost point the x-coordinate is pi squared over 4 minus 5. The y-coordinate is 2. So there's our northernmost point. At that highest point, is the train moving left or right? Okay, to find out if the train's moving left or right, we just need to horizontal motion is governed by our x prime. So x prime we saw was 2t. So let's figure x prime at pi over 2. That's equal to 2 times pi over 2. And I'm not really concerned about what the answer is here. I'm just concerned, is the answer positive or negative? Clearly this is positive. So at the highest point, the Snowpiercer is moving right, which is east. Last, we're supposed to find all points of inflection. So let's figure out our what do we call this? Our second derivative, d squared y dx squared. So d squared y dx squared is equal to the derivative with respect to t of the slope. Let's remember that the slope was cosine t over t. I'm going to make sure I got that right. Cosine t over t over dx dt, and we already said dx dt was 2t. So now we just got to figure out the derivative of cosine t over t. That sounds like a quotient rule to me. So it's denominator t multiplied by the derivative of the numerator, which is negative sine t, minus the numerator multiplied by the derivative of the denominator, all over the derivative squared. Okay, divide that by 2t, and that's an expression for the second derivative. You can clean that up a little bit, and I'll definitely clean that up a little bit. That is negative of the quantity t sine t plus cosine t divided by 2t cubed. And so we need to know when this is equal to 0 or undefined. Okay, so I'm going to go ahead and grab my calculator. And let's change this to our, well, no, let's change it to the function mode. And let's graph our second derivative. Our second derivative was negative of t. Was that sine or cosine first? Don't remember. Sine first. T sine t plus cosine t. That whole thing divided by 2t, that's not a t, 2t cubed. Okay. So we just need to graph this with t between 0 and pi. So 0 to pi. And we want to know, when is this derivative equal to 0? When is it undefined? I think I'll change this from negative 10 to 10 just to help me here. And well, let's graph. Let's take a look at our derivative, second derivative. All right. Oh boy, here we go. It's taking a long time to cross the axis here, huh? Wow. Well, that's not going to help us find it too much. I think maybe we should do a quick analysis here. I don't know why, but I think it goes over the axis and then below the axis. This seems as though as we go further to the left, this is going to get vertical. So I don't think the second derivative is going to exist as t approaches 0, really. And if you take a look at the equation, that makes sense. This second derivative doesn't exist when t is equal to 0. So in order to see that, let's just exaggerate this vertically, and we'll go from negative 0.5 to positive 0.5. Oh, syntax. Negative 0.5 to positive 0.5. Do a graph of that. No guarantee this is going to help. Okay, can we perceive when it crosses the axis, if it crosses the axis? Okay, so it does cross the axis just that one time. Let's figure out where that is. We're going to second calculate. We're going to look for a 0. Somewhere between, oh, I don't know, this is somewhere between 2 and I know that that's pi on the other side, so I'll just put in a pi. Somewhere between 0 and pi. And let's just take a guess, maybe right around here. All right, 2.79838. Okay, that's at t equals 2.79838. Okay, second derivative goes from negative to positive. So we have a point of inflection at t equals 2.79838. All right. Finishing up here with arc length, we've got a function defined parametrically. We can get the arc length with this equation, which looks a lot like you're integrating the Pythagorean theorem, and you kind of are. So, let's do this. The graph of the graph of an asteroid is, I keep wanting to say asteroid, which is like that really cool video game from 1981, which you probably never played. Graph of the asteroid is given by a parametric defined equation. X equals cosine cubed t, y is equal to sine cubed t. T is between 0 and 2 pi. Graph the asteroid noting starting and ending positions of travel. Okay, so this is going to require us to take our function and put it back into parametric mode. Let's go back into parametric mode. Go back to y equals, and then we're going to put in our graph. We just need to take our cosine and cube it. And then we take our sine and we cube it. And let's check out our zoom again. No, it wasn't zoom, it was our window. 0 to 2 pi. X min, I think I'm going to need to go further down than that. Let's make that -2. No, we had pretty good success with -3 to 3. And then our y min from -2 to 2. And let's just graph this asteroid. Take a note of the starting and ending places. All right. Ooh, that's a really cool graph, actually. I like that. So it started at 0, 1, and then it went up, down, down, up. All right, so we can graph that real quickly. Here we go. Nothing too fancy. Up, down, down, up. This is start and end. Start, end, direction of travel. There we go. Number 2, find the arc length of this asteroid. Okay, so for our arc length, we're going to need x prime and y prime. So x prime is equal to 3 multiplied by cosine squared t multiplied by the derivative of cosine, which is negative sine t. Y prime, that's going to be equal to 3 times sine t square of sine t multiplied by the derivative of sine t, which of course is cosine t. Okay, so the arc length then is that's going to be equal to the integral from 0 to 2 pi, and we'll take actually we're going to put this in parentheses because I like this better this way. -3 cosine squared t sine t, this whole bugger squared, plus 3 sine squared t cosine t, this bugger squared, and then we'll take this entire thing to the 1/2 power dt. So let's just make sure. Let's see. Do we have a square root? Yeah, we have the square root. Do we have the derivative of x squared? Yeah, we have the derivative of x. It's squared. Plus, okay, it's a plus. The derivative of y, did I square it? Yeah, I did square it. So here is my arc length formula. Now I'm going to go to the calculator and calculate that. Let's get back to the home screen. And actually, I'm about to do some math, so it's better to be in function. Okay, and now that we're in function, we'll go to the home screen and we'll integrate. We're going from 0 to 2 pi. Okay, and then my x was negative 3, oh, was it sine or cosine? Cosine squared. Cosine? Yeah, cosine of x. I had the caps lock on if you were wondering. Cosine squared x multiplied by sine of x squared. Oh, I don't have nearly enough parentheses here for this, guys. That looks completely wrong. So I'm going to abort right now before this gets any stranger, and I'm just going to put them here. Okay, so negative 3 cosine of x squared multiplied by sine of x. And then this was going to be 3 sine of x multiplied by cosine of x. Great. And let's go back into the home screen, and we're going to do y1 squared plus y2 squared. Keep it simple. And cool. y1 squared plus y2 squared. Dx ooh, look at that calculator go. All of that for 6. Okay, so the arc length is 6. Isn't that exciting? And that's the end. We're going to have a separate video for the rest of this, because I think that, you know what, let's just go ahead and do the whole thing now. Okay, so here are the things that we're going to be looking at for your in the box important ideas. We got the idea of a parametric curve where every position is given by a function of x and y. For a independent variable t somewhere between a and b. We've got over here, we've got the idea of slope being dy dt over dx dt. Here's that equation for second derivative. Here's the equation for arc length. And as we graph, we need to show start, end, and direction. You can pause it here if you want to take all that down. Of course, you know what to do. Okay, and we're going to go ahead and try to figure these out. We've got the track of Snowpiercer is parametrically defined by cosine t and root 2 cosine t between 0 and 2 pi. First, we're going to sketch that graph. We're going to find the equation of slope, and then we're going to find all the times t where the tangent to line to the slope, or sorry, tangent line to the graph is either horizontal or vertical. Find the inflection points, and we're going to find the length of the track over the domain of t. So those are some really, I guess I could say gnarly here. So these are pretty gnarly problems. The first one, to graph that, we're going to sketch it. Again, this is kind of like if you're going to sketch this by hand, go crazy, figure out all of the t values here between 0 and 2 pi. But in the interest of time, I'm just going to go ahead and do that on the calculator for us. Okay, so I'm not in parametric mode yet. I should move to parametric mode if I want to graph this. Okay, now we're in parametric mode, and let's graph that. Our x function is given by cosine t. Cosine t, oh, I should clear that out first. There we go. Cosine t. Our y coordinate is given by root 2 and then cosine t again. And then now we're going to graph this between 0 and 2 pi. 0 and 2 pi, okay. I think I saw a square root of 2 there. So do I, yeah, I think I exceed a square root of 2 in all directions. So let's just graph that. Oh yeah. Oh man. So it starts up over here in the top right hand corner, comes back down, and then comes back up. Alright, so that's going to be a challenge for us to graph. So, okay, so that's not a very elegant looking graph that you see that we've drawn over here. We've got a start and the ending. Arrows are numbered to show that it's going to go all the way back down and then all the way back up again. Okay, so for the equation, find the equation of m, the slope of the graph at time t. Find all times with t when the tangent of the curve is horizontal or vertical. Okay, so first of all, we're going to find the equation of the slope. Okay, so as you can see, the derivative of y is negative root 2 sine t. The derivative of cosine is, the derivative of the x coordinate is negative sine t. These all cancel out. That gives us a value of the slope of square root of 2. So basically, the slope of this is always square root of 2. And if I take a look at my curve, well, yeah, that slope is always square root of 2. So what are we saying? No vertical, no horizontal tangent lines. So that's B, that's A. C, let's find all inflection points. So that's going to start off with finding our second derivative. I'm going to pause here for you to do that. Actually, no, that's not that hard at all, because we're going to take the second derivative is equal to d dt of the slope and divide it by dx dt. Well, the slope is always square root of 2, and square root is always a square root of 2, and the derivative of the square root of 2 is 0. So that means that our second derivative is always equal to 0. So are there any inflection points? No, there are no places where the inflection changes or where the concavity changes from positive to negative or negative to positive. It's just a constant second derivative of 0, so no inflection points. And lastly, find the length of the track over all the domain. So the length of the track is going to go from 0 to 2 pi, square root of dx dt, which was negative sine t squared plus negative root 2 sine t squared dt. Let's put that in our calculator. I think I can handle this from the home screen now. Maybe I learned my lesson. Math 9. We're going to go from 0 to 2 pi. Square root. The first one is negative sine t. Squared. The second derivative is negative square root of 2 sine t squared dt. Great. 6.928. So the length equals, and I gotta find my cursor here. There we go. So d, the length equals 6.280, no, totally forgot, 6.92820. 6.92820. All right, and that is everything, folks. That was a long one. Hopefully they're not going to be so long in the future, but that's it. I will see you later. Enjoy your calculus and get started. Bye.